In geology, weathering means physical and chemical breakdown of rocks and minerals at and below the earth's surface. Rocks and minerals formed by igneous and metamorphic processes, which are on high temperature pressure conditions, lose their stability as soon as they are exposed on or near the surface where pressure temperature conditions are low and there is abundance of oxygen, carbon dioxide, water and biota. We shall discuss the topic concerned under the following heads: chemical weathering, weathering products, colloidal deposition, residual deposits, that is mainly bauxite, and we shall see residual deposits other than bauxites. Chemical weathering and mechanical weathering, that is also known as physical weathering, go hand in hand. In fact, the two processes help each other. Mechanical weathering is responsible for the physical disruption of solid rocks, minerals, and factors that affect it include geology, including structure, then time, thermal expansion, relief, wind, water, ice, root, salt wedging, burrowing animals, and even microorganisms. Physical weathering alone could produce or tin, tungsten, diamond, and others hard ore minerals like thorium deposits. Various agents of chemical weathering include water and its dissolved constituents, which is owing to its unique properties, oxygen, carbon dioxide, together with chlorides and sulfates derived from ocean, and anthropogenic contributions, which includes domestic and industrial waste. Dissolution is thus the stage for chemical weathering when minerals are dissolved into water. Minerals most affected are salts and carbonates, but even silica minerals and silicates are dissolved to some extent. The entire process is rather complicated and involves a number of interrelated processes, quite often working together. These includes hydration, hydrolysis, oxidation, the action of acid, dissolution, colloid formation, and exchange reactions. Hydration simply means absorption of water on the surface or in its crystal structure of rock or a mineral. Anhydrite, for example, composition CaSO4 on hydration will produce gypsum CaSO4 2H2O. Hydration leads to hydrolysis, which is a reaction between mineral matter and water, splitting the mineral into two or more products. For silicate minerals, absorption of water is the prerequisite for hydrolysis. Water, when absolutely pure, may cause little damage or decomposition of the mineral kingdom, but in the presence of natural acids, that is carbonic acid being the most common, and alkalis becomes a potent solvent. Hydrolysis works faster in acidic water. Carbonic acid in the presence of water will react with, for an example, a common mineral like feldspar, and it will produce a clay mineral which we call kaolinite, and releasing potassium ions and bicarbonate ions, and also it dissolved silica. Oxidation occurs in aerated environment, as oxygen of the air in presence of water combines with minerals to form oxides. Minerals containing ferrous or manganese ions are specially susceptible to this kind of decomposition, and resultant minerals with higher valency oxides are formed. Rust, the coloring agent of many rocks, minerals and soil, is the best example. Iron minerals like pyrite on oxidation produce sulfuric acid, which further hastens the process of chemical decomposition. Oxidation generally is limited above the water table, but oxygen rich water percolating below the water table can oxidize far below the water table. Carbonation is extremely useful in hastening chemical decomposition. Carbon dioxide present in air, water, soil unites with minerals, converting them to carbonates and bicarbonates, which are easily soluble and thus are carried away. Water combining with carbon dioxide produces carbonic acid. Exchange reaction involves absorption of ions present in the aqueous phase onto solid particles. Particles are exchanged and removed, and thus making new mineral species. Nature of cations and ions present, pH of the systems are the controlling factors. Biologic agents, namely root system and microorganisms, play a very important role during chemical weathering. Weathering products of rocks, minerals and ores take three forms. Number 1, resistates or stable residual primary minerals. Number 2, secondary minerals formed and that remain stable in the weathering environment. And third, soluble cations that are removed by circulating waters and which in turn may form new ore minerals by precipitation or evaporation. Before considering each of these separately, we need to look into the summary of the fate of primary rock forming minerals when they are subjected to weathering agents totally. This was presented by Fields and Swindale in 1954. Further, one must remember that as early as 1938, Goldish pointed out that the order of stability of minerals formed under igneous regime is the reverse of the order they are formed, and as presented by N.L. Bowen in 1928 in his famous reaction series. In the zone of weathering, minerals that are hard and remain unaffected by the chemically charged percolating waters. These include quartz and other resistant accessory minerals like zircon, swene, monazite and others. Clay minerals that are stable under the secondary environment, as also hydromicas, may stay back at their original site, that is in the regolith. Ore minerals like gold, cassiterite, wolframite, monazite, magnetite, ilmenite and rutile are the important resistates. These may, however, be carried away as detrital grains by physical weathering agents. Leaching of the primary minerals of rocks and subsequently hydration and hydrolysis produces secondary minerals, which are extremely fine grained, less than 0.02 millimeters, and includes clay minerals which are hydrous silicates of aluminium, iron and magnesium. There are four important groups. Number 1, kaolinite. Number 2, montmorillonite. Number 3, ilites, also known as hydromica, and chlorite. Kaolinites are favored in acidic rocks like granite under acid environment where drainage is free, while montmorillonites are favored in basic rocks under waterlogged conditions of the ground in semi-arid climates. Hydrous oxides of iron and aluminium are the most common weathering products under humid tropic climates. The most important minerals include limonite, tergite and goethite, and two members of the all important product, that is bauxite and diaspore, which are hydrous aluminum oxide and of course gibbsite. Soluble products that are removed from the site of weathering will naturally depend upon the composition of the parent rock and of course on the existing physico-chemical conditions. It will be calcium, magnesium and carbonates if the parent rock was calcareous. In case of igneous rocks, it will be alkalis and alkaline earths and also silica, both in ionic as well as colloidal form. Proportion of these constituents will depend upon the nature of the rock, whether it is felsic, mafic or ultramafic. Granites, argillaceous sediments and schists will release more of sodium and potassium, while it will be magnesium and calcium if the rocks are mafic. Elements removed initially are likely to be removed by adsorption on clays. For example, potassium in the case for halite in preference to sodium, which will remain in solution for a long time. Iron and manganese get dissolved together in reducing conditions, but iron get precipitated under oxidizing conditions sooner than manganese. Apart from EH and pH of the environment, relief and drainage conditions of the area also controls retention of some elements in the solution or their deposition with the clays. Depending on these conditions, soluble products removed from the weathering site will take their own route and time for the removal from the aqueous system as secondary mineral deposits. A word about colloidal state is in order. Colloidal state is a subdivision of size and particles are generally multimolecular. There may be three types of colloidal systems, like in smoke, which is a solid gas mixture, or fog, which is a liquid gas system, and emulsions, which is liquid system, and salts, gels and pastes, which are solid liquid systems. The last system, that is salts, is of much interest in sedimentary process. The particle may range anywhere between 10 raised to minus 3 to 10 raised to minus 6 millimeter and are electrically charged. There are colloids with positive charge. Negatively charged colloids include silica, vanadium pentoxide, manganese dioxide hydrate and humus colloids, and of course sulfide salts. Ferric hydroxide is unique in this case, as it can acquire both positive or negative charges depending on the way it was formed. It is now believed that silicates, the most important members of the igneous rocks, are also decomposed. Even silica and alumina for a short while make true solutions, which on aggregation of ions make colloidal sized clusters. To begin with, these clusters are amorphous, but with aging turn into clay minerals that have definite crystal lattice. Phyllosilicates like muscovite and biotite, without breaking down, may change into other clay minerals directly. Colloidal deposition of minerals and ores, though not so well understood, has many examples. Coliform habit of ores and minerals has been generally considered as a proof of colloidal deposition. Mineral habits like botryoidal, mammillary, reniform, nodular and pisolithic are attributed to colloidal deposition process. Minerals like opal, even after deposition, remain in amorphous state, but many others may acquire some degree of crystallinity, becoming metacolloids. Examples include malachite, marcasite, silomelane, smithsonite, bauxite, chrysocolla, and quite often they may attain radial structure. As the name indicates, these are components of the earlier rocks left in situ. Once the lighter and more soluble mineral matter is washed away, in the equatorial and tropical regions of the world, where temperatures are high and rainfall heavy, this process is very common. Such tropical weathering products are known as laterites. When laterite is nearly pure aluminum hydroxide, it is called bauxite, which is the chief ore of aluminum. Any rock which has some alumina to start with can become the source material for laterite and bauxite formation. It is more the extent of tropical weathering and leaching away of unwanted constituents from the source rock that make a bauxite deposit. The term bauxite derived its name from Les Baux de Provence, a locality in southern France, and was formerly considered as an amorphous clay minerals with a composition of aluminum hydroxide with water molecule. It is off-white or grayish brown or yellow or reddish brown in color. Principal mineral constituents are gibbsite, boehmite and diaspore, with free silica, salt of iron hydroxides and clay minerals. Younger bauxites, that is in age, are generally gibbsite rich, while the older ones are richer in boehmite and diaspore. Ordinarily, chemical weathering of feldspars in alumina rich igneous rocks yields kaolin. However, in tropical to subtropical monsoonal climate conditions, the weathering is carried a step further with the removal of silica and thereby enriching the residue in hydroxides of aluminum, iron, manganese and titanium. Most favorable pH of waters draining the area of interest for the removal of silica from alumina is between 5 to 8. Temperature of around 200 degrees centigrade is desirable for bauxite formation. A further refinement in pH of about 3 with low EH then removes iron also, and the residue is alumina rich bauxite. Geologically, bauxite deposits are divided into 3 categories: upland or high level bauxite, which are also called blanket deposits, are confined to tropical regions on high plateau, as are fairly thick up to 25 meters. Deposits of Ghana, Guinea, India and southern Queensland, Australia come under this category. Low level bauxite lie along the coastal tracts in tropical regions and are thinner, only up to 8 meters. Karst bauxites are generally older in age, that is Paleozoic to Tertiary, and are developed on the karst-like surface of limestones and dolomites, generally in the form of pockets. The West Indian and the Mediterranean bauxites come under this category. Most of the world's large deposits were formed during Middle Cretaceous to Middle Eocene times, though the one in Spain is formed in Devonian rocks, while those of Croatia are Triassic in age. Deposits from India, Brazil, New Guinea, Malaysia and Dominican Republic all belong to Tertiary to recent times. There was a very favorable climatic condition from late Mesozoic to Tertiary times that favored bauxite formation. Residual iron-rich laterites. World has substantial reserves of high iron ores, high-grade iron ores in banded iron ore formations and other chemically precipitated. Therefore, presently laterites may not be considered favorable resource for iron presently, but most basic and ultra basic rocks in suitable climatic and topographic conditions yield iron rich laterites if not bauxites. Occasionally, they may be sufficiently iron rich and useful trace elements like chromium, nickel and titanium, which could be won as byproducts should these huge lateritic covers round the world be used as a source of iron in future. Presently, their use is only as construction and road metals. The second type of deposit which comes under this category are residual nickel deposits. Ultra basic rocks contain large amounts of nickel between 1000 to 2000 ppm respectively. Weathering of such rocks in the tropics gives rise to nickel rich laterites, which constitutes a good source of nickel ore. In fact, it has better potential than even the magmatic nickel deposits of the world, and the first commercial production of nickel came from such a source in New Caledonia way back in 1876. A typical profile through nickel rich laterite deposits in New Caledonia is illustrated, where nickel after being dissolved quickly gets reprecipitated on iron minerals or may form nickel rich micaceous minerals. There is always some amount of cobalt with lateritic nickel deposits. All the three deposits discussed need the following requirements. Number 1, the ore minerals sought should be insoluble. 2, the unwanted minerals be soluble. 3, topographically the region be flat without high relief so that the desired components are not washed out. Geologically speaking, the area should have been stable, which provide more time for residual processes towards completion. And 5th, climatic conditions be favorable, preferably tropical monsoon or Mediterranean type with high rainfall. The theme of chemical weathering, colloidal processes and the resulting residual deposits all work together in secondary environment, which is rich in water, oxygen, carbon dioxide and biota. These work to decompose and leach the early formed rocks and minerals, while soluble products are carried away and with proper change in physico-chemical conditions will get oxidized as chemical precipitates of iron and manganese ore deposits, for example. What remain still soluble in the aqueous will ultimately become an evaporite deposit like that of gypsum, carbonates or potash and others. I hope you have learned something on these three interrelated processes that produce some of the useful ore deposits of the world. Thank you.